that are not moving. That's your static situation. They are not in motion. Involves concepts of static pressure, buoyancy, Pascal's law. Okay? Once a fluid starts to move, okay, then everything changes. We are assuming, when we apply Bernoulli's law, which is the rule for fluid dynamics, that we are in what is called streamline flow. So literally our fluid is traveling along lines. Okay? And then we can use Bernoulli's principle. If there is any turbulence whatsoever, then Bernoulli's principle goes out the window, and then things really get complicated. You'll all be probably taking classes in college on fluid dynamics and seeing just what turbulence can do in trying to figure out these things. I mean, you will spend hours doing a turbulence problem.
I can't wait.
There's a lot of things, which is beyond the range of what we're doing. So we're assuming streamline flow for any of this. Bernoulli applies to streamline flow. It just says that pressure before is equal to pressure after. But for Bernoulli, because we are now in motion, your pressure can come from a number of different sources. Your pressure can come from just any outside source. Your pressure can come from the height of your fluid. Your pressure can also come from the motion of your fluid. So, Bernoulli's principle is that the outside pressure plus the pressure due to the height plus the pressure due to the motion, this is velocity here, this is density, this is density, this is just pressure from any source, is a constant. Now what this translates into is that P plus rho VH, rho GH, plus 1/2 rho V squared is equal to P plus rho GH plus 1/2 rho V squared. And you get into situations like this, okay, where I've got streamline flow, okay, but note that the size of my pipe is getting smaller. Okay? Well, we know from the other day, our fluid continuity, that the volume stays the same. Your volume in is equal to your volume out. Your volume for a fluid that's in motion is equal to the area, the cross-sectional area through which it flows, times the velocity. So A1 V1 is equal to A2 V2. This is your fluid continuity. So the cross-sectional area times the velocity at one part of the system has to equal the cross-sectional area times the velocity of the other part of the system. Now, if we take a look at the problem on the front page. Water throws through a non-uniform pipe. The initial velocity of the water as it enters the pipe is 5 meters per second. So here's my pipe. There's my pressure gauge. And then I have another pressure gauge down here. And then I have another pressure gauge over here. I'm told that moving at 5 meters per second, my pressure is 100,000 pascals. First question is, what's the pressure on gauge 1? Well, the pressure on gauge 1 is 100,000 pascals. What's the water velocity at number 2? Okay, well here's number 2. I've got a double step down here. Well, because my cross-sectional area is getting smaller, okay, then I know my velocity times my area, 1 has to equal my velocity times my area 2. Well, area 1 is 50 square centimeters. Its velocity is 5. Area 2 is 40 square centimeters. Solve for its velocity. Velocity comes up as 6.25 meters per second. Note that it speeds up. It goes from 5 meters per second to 6.25 meters per second. So that the volume stays the same because my cross-sectional area gets smaller. Then what is my pressure at gauge 2? Well, the pressure has to stay the same. But the pressure is a function of the velocity, and the velocity is changing. So my initial pressure, which is 100,000, plus my rho g h is effectively 0 because my pipe is literally horizontal, so it's not changing height, plus 1/2 times rho times 5 squared has to equal my pressure plus rho g times 0 plus 1/2 rho times 6.25 squared.
Why is the pressure 0? Why is the height 0?
Because effectively my water is not changing height. So, you know, that little bit, which would be the little bit that the pipe is changing, won't make a difference. On something like the one on the back of your page, that's where height plays a big difference. You can see that the height is changing considerably as you go uphill. Okay, so you substitute your numbers in. Rho is 1,000. Okay, so here you end up with 100,000 plus 0 plus 1,000 times 25. So you end up on this side with 112,500 pascals. On this side you end up with P plus 19531. So what's the pressure on this gauge? The pressure on that gauge is 92,969. Because this plus this has to equal to that.
Please pardon this interruption.
Do the same thing down here.
Men's basketball
Velocity
practice
times area,
will
velocity
not
times
begin
area.
today until
Velocity
3:45.
here.
And there are 4 bus changes. 5718 will be 5691. 5668 will be 5520. 5475 will be 5576. And 5476 will be 5627. Thank you and have a good day.
Plug your 8.33 in over here. The initial conditions haven't changed. Solve for what's happening with the pressure here. You have the pressure there is 77,000. On the back of the
Right,
page,
Josh?
the only difference is